Hello everyone, and welcome back to another Eng130 video tutorial. In this tutorial, we're going to stay on the concept of particle equilibrium, and more in depth, we're going to go into springs still. But in this example, we're going to go a little bit more in detail on the spring formula so that there's no questions, no concerns about it. Because that spring formula, as I said, it's kind of tricky. It got me a lot when I was in first year, and I know that just some extra clarity on it could never hurt. So that being said, let's begin. Alrighty, so looking at this example, it wants us to determine the mass of each of the two cylinders if they cause a sag S of 0.5 meters when suspended from the rings at A and B. Note that S equals 0 when the cylinders are removed. So that's very important, and this will have to do with trying to find the force in the spring, as you guys will see a little bit later. But before we touch on that, I'm just going to show you guys something which will make this example a lot easier. And that has to do with symmetry. So if I were to if I were to draw a line right down the center, this is perfectly symmetric. So what that means right here is at point A and at point B, each one of those points has three forces. So we're going to have a force going down at both because of the mass of the cylinder. We're going to have a force coming across like this. We're going to have a force coming upwards like this, going along the spring. But this is really nice because everything is symmetric, because it means that this, let's say F1 at the bottom, then this one's the exact same F1. If this is F2 coming across, then this will be F2. And same with this, F3, F3. But this is a very special case, and it has to do, and it's because of a multitude of reasons. One, the springs are spaced at the same distance apart. Each spring has the exact same sag, and that's because the K value of each of the springs are the same. Now, if the problem were to have this as, let's say, 4 meters, this would not work. Let's say that one of the springs was 100 newtons per meter and the other one was 200, this would not work. So this is very important to note that this is not for every scenario, but for our scenario, this makes it really easy. And even if it was the second scenario where we'd have to go through and find the rest, it's actually not that bad. I'm just showing you guys this because the point of this example is to get more familiar with the concept of the springs, which will work out very nicely. So what I want to do right here is the first thing I want to do is I'm going to draw a free body diagram at point A. 'Cause like I said, we're only going to analyze one of the sides. So that's going to be our point A. So what I'm going to do is I'm going to draw a point A here. And then again, to find the forces, I think the best way to do it, if you're unsure, and for this it's pretty easy to tell, but when it comes to beams, this box will actually make a lot more sense, and you guys will go, oh, okay, that's why he's doing it. Because beams can be a bit more complicated. So right here we see that it intersects 3 times, so we're going to have 3 forces. So when we look at A, there's a force coming down, which is pretty obvious, so I'm just going to put an arrow going down. We have one that goes straight across, as so, like this. And then we have one that goes up, kind of to the corner, like this. Perfect. So what I like to do is just label all these forces. So this force 1 here, it goes from A to B, so I'm just going to put force AB. The force AC, well, that's the spring force. So what I'm just going to do is, because we only have one spring in this equilibrium, is I'm just going to go FS. So the force of the spring. And then finally, this last force, as I showed you guys in the previous example, how to prove this, but we know that this is just going to be the weight of the cylinder, which is equal to the mass of the cylinder, which is what we want to find in the end, times gravity. Now, if we look at this free body diagram, we're missing 2 things. And one is just going to be the geometry of this force, since it does come at an angle. So if we look up, we see that it goes 2 meters across. And if we look at the sag S is 0.5, so we know that this is also 2 meters. And like I said in the previous example, if they're both equal, which we have in this case 2 and 2, we can just take those away and go 1, 1, root 2. So all the geometry is now accounted for, and I probably just put right here, I'm just going to write free body diagram so everybody knows what I'm doing. And then the last thing we have to do is just state our directions by putting a little axis here, like this, and ta-da, So this will be my positive x, my positive y, and then positive rotation. But again, particle equilibrium, we don't deal with rotation, so everything is kind of nice. So if we look at this right here, we have 3 unknowns. So typically, we're not going to be able to solve this equation, but that's fine because I'm going to show you guys 2 tricks. So one, if we're ever given a spring, typically we can solve for this force, this Fs force. So if we know that Fs force, then we have 2 unknowns and we're good to go. However, I want you guys just to kind of think ahead a little bit. We're going to find Fs, of course. It's a spring force. And we're interested in this mass. And what's nice about this mass is the force associated with it, that Wc, it's strictly vertical. So the only equilibrium equation we should need for this problem is sum of the forces in y is equal to 0. Because if we were to do sum of the forces in x, that weight would have no component, so we wouldn't be able to solve for anything. We'd be able to solve for, and I'm just going to put this in a different color, we'd be able to solve for this FAB, but that's not a part of the question, so honestly, who really cares? We don't need to solve for it, let's just leave it alone. So if we were to do sum of the forces in the x really quick, in the y, what we're going to have is the spring force is going up, so it's positive, and we want its vertical component, so it's going to be 1 over root 2, and that's equal, I'm getting ahead of myself, but I shouldn't. I need to show you guys everything. So it's going to be minus the weight of the cylinder, and it's minus because the weight of the cylinder is pulling downward, and that's going to be equal to 0 since it's in static equilibrium. So what we can do is we can rearrange some things and go that the force of the spring divided by root 2 is equal to mass times gravity. And we can rearrange this further to find that the mass of the cylinder, so this is what we want in the end, we can find that if we know the force of the spring and then gravity times root 2. So here's the formula that we're going to use to solve the whole question, and this is not working too nicely, but that looks fine. So if we look at this formula here, just kind of checking the boxes of what we know, we're looking for m, so this is perfect. We have a formula for m. We know gravity. We know root 2. Well, hopefully we know root 2. So the only thing that we need is the force in the spring. So what we're going to have to do is find the force in the spring. And let's find a different color. Let's find a nice fun color. I don't want you guys to associate the spring force as a very negative color. So the force in the spring, what we can do is we can find the force of the spring using the spring formula, which I said is going to be equal to a constant k times its relative stretch. And that could be expanded further, like I said in the last example. So if this is throwing you guys off, I recommend just going to the last example. I explained this a little bit more in detail. So what we're going to have is that delta x is equal to its new stretched length, so the total stretched length, minus its original unstretched length. And if we look up at the question here, we're given k, so I'm going to write just kind of underneath. We know that k is equal to 100. So if we know k, so we can find the force in the spring if we can determine both its fully stretched length and as well as its original length. And we can do that very nicely using I'll draw it in a box here, using this geometry here. Not a very nice box, but I'm just going to erase it because I'm going to draw it down here. So what we have is basically 2 triangles. So we know that the horizontal length of the spring does not change. It's going to be 2 meters the whole time, stretched or unstretched. So what I'm going to do is I'm going to draw 2 meters. So this right here is kind of where that point is, and this is going to be 2 meters. And we know that the spring has 2 scenarios, the stretched and unstretched. So I'm going to do the stretched first, and we know that the stretched length comes up a distance, oops, that's not what I wanted. I wanted this one, perfect. We know that the stretched length comes up a distance of 2 meters. So this is also 2 meters. So what's nice about this is the stretched length of the spring. So we know that this right here, this distance, that hypotenuse there, that's actually going to be equal to the L that we want, the stretched length of the spring. the spring's length after it's stretched. I don't want to say stretched length because usually that means like the relative stretching, so the distance between the unstretched length and the new length. So it can be kind of confusing really quick. But we know that we can find L is equal to the square root of 2 squared plus 2 squared. So that's going to be 4 plus 4 is 8. So L is going to be root 8. And of course L has units of meters. So that right there is its length after the load, so it's stretched length. But then we have the second scenario, the unstretched length. And in this case right here, we know that that vertical distance isn't 2 meters. It's actually 1.5 meters. So I'm going to go 1.5 meters for that distance. And we know that this right here, oops, is going to be L naught. So it's unstretched length. So if I go L naught here, and that's just going to be equal to the root of 2 squared, so that horizontal component doesn't change, but the vertical one does. So plus 1.5 squared. What I'm going to do is end my bracket there. And what I get here is this one's equal to 2.5 meters. So 2.5 meters. So since we know L and L naught now, we can go right into the spring equation and determine the force in the spring. So the force of the spring is going to be equal to 100. So this is the constant K. And it's going to be L minus L naught. So what we're going to have is root 8, which I think is like 2.8. 2.8. You guys can correct me if I'm wrong. So 2.8 minus 2.5. And what we get is that force in the spring is equal to 32.84 newtons. Perfect. So now if we go up to the formula over here, which I'm going to highlight in the pink, I find the pink really shows the best. So if I go back to this formula, we can find the mass that we're interested in since we now know the force in the spring. So our mass is equal to, and I'm just going to write the formula down again so you guys know exactly what I'm doing. It's going to be the force of the spring times divided by gravity times root 2. So let me just do that. And then what we get when we substitute everything in is gravity is going to be 9.81. And then root 2 is just root 2, nothing special. And up top, what we get is 32.84. When we type all of this into our calculator, what we get is the mass is equal to 2.367, 2.367, dot, 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 and that'll have units of kilograms. So the last thing that we're going to want to do, and I'm just going to do this in a more bold color so everyone can see, is we're just going to write the mass of the cylinders to cause this deflection in the springs is going to be 2.37 kilograms. And I'm just going to box my final answer because that's the final answer. So again, this example is not too bad. It's just making sure you guys know what to do with the springs in that spring formula. And just as a quick example, I'm actually just going to put it here so I can really drill this into your guys' head with springs, because if you guys remember this, you guys will be fine. So if we have an unstretched spring, and this was drawn in the other one, so this is the unstretched spring. So this distance here is its unstretched L naught. And we have a second spring. So it's the same spring, except now it's stretched. Something, let's say, like this. And this distance here, oh, come on, I want this nice and straight. And we have this distance here, and this is its new current length, L. Actually, that's probably the best way to say it. When I'm referring to L, I'm going to say the current length of the spring. So that's going to be L. L naught is the original length of the spring, and the stretch in the spring is going to be this distance right here. So this right here, this is going to be the delta X. So that's the best way to remember springs, because once you guys get that, you guys can just go back to this formula up here, and everything will be nice and easy. So it kind of throws you off at first, but once you guys figure it out, it's pretty simple, because I know that you guys are experts on getting forces now. And now that you know how to get the forces, you can easily find the deflection of springs. So it's really nice. It's a nice tool to have. So that concludes this video, and in general, springs overall. This week we have 2 videos left. The next one's going to be multiple pulleys. It's not a hard example, but I know when there's a lot of situations on the page, students can kind of get confused, so hopefully it's just to clarify that. And then the last example, which I'm going to recommend spending a lot of time on, is particle equilibrium. So everything we've done so far, but no springs, nothing like that, but in 3 dimensions. So 3 dimensions is really, really crazy because there's a lot going on. There are some nice tricks to it to make it easier, but I'll let you guys decide what makes it easier for you. But that's one I recommend the most because between us, I think that's the one that you will probably, I'm going to say 90% will see on a midterm, something like that. That's what it usually is. All right, guys, so thank you so much for listening, and I'll see you guys in the next video.